Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I am learning quickly, I don't claim any real expertise. Today, we're looking at the 51st Project Euler problem. As always, I will link to the problem and my repo in the description. Let's dive in. Problem 51 is prime digit replacements. By replacing the first digit of the two-digit number *3, it turns out that 6 of the 9 possible values are all prime. By replacing the third and fourth digits of 56**3 with the same digit, this 5-digit number is the first example having 7 primes among the 10 generated numbers, yielding the family, etc. Consequently, 56003, being the first member of this family, is the smallest prime with this property. Find the smallest prime which, by replacing a part of the number, not necessarily adjacent digits, with the same digit, is part of an 8 prime value family. Okay, so this is actually the first problem that I've gotten to that's rated at a higher difficulty. It's still not super high difficulty. It's 15% instead of 5. But looking at this, feel like it isn't so much the problem itself that is difficult, but doing it efficiently. So, for instance, I think a basic approach with this would be to first populate prime Boolean array. For each prime let's say for each prime do all possible replacements. So like for 56003, check how many are prime. When we get to a number with 8, meaning the conditions, stop and show the smallest prime. Okay, so another note here So for an 8 prime value family, the smallest prime should have 2 plus occurrences of the digits. Let's see, so it could be 0 or 1 or 2. Because otherwise, either we've already checked it by doing this, finding the possible replacement numbers, or it can't possibly be part of an 8 prime value family because we've checked the version with the 0s, 1s, and 2s. So I think that this is going to be the key to our efficiency here. I'm going to end up using something similar to what we did last time, or last problem. I'm just going to go ahead and copy all of the code here. So let's see. So limit of 1 million. Okay. Going back to the problem for a second. Okay, so let's start by looking in the 2-digit numbers to see if we can get 13 and go from there. Okay, so we have our little timestamp. We have a limit of 100 because we are going to start looking just for 13. Oh, that's not how you do comments in Java. Let's see. 5-digit number, other one, so if we do a 6-digit number, it should give us the 56003, and that is going to be the next check that we run once we are confident that this works for 100. Okay, so we have that. We create our Boolean array where everything is set to true, set the first 2 values to false, go through all of those values up to, in this case, like 11, and check off all of the or set to false everything that is not prime by starting with the square of the prime, so 5 would start with 25, and then just continue adding 5 to 25 and setting all those values to prime until we hit the limit. And now, let's see. This problem, the logic here is going to be somewhat different, obviously. Let's see. So for I in range limit, if is prime, then we want to see how many see if we can find 2 or more zeros, ones, or twos. So I'm just going to go ahead and do it that way. Okay, so find if I has 2 plus. If so, find other numbers in the family. Check whether each has doop-doop-a-doo. Count how many are primes. Okay, so limit equals 100. Target equals... Okay, so I'm adding this other variable called target, and what this is going to do is going to allow me to make this a little more dynamic. Under 100, if the limit is 100, and we're looking for 13, because 13 has 6 out of 9 possible values, so we are looking for something with 6 prime numbers in the family. And the digit below, it's actually going to be 10 minus target. So for this one, since we're writing the program as we don't know the answer, even though we do, the program shouldn't. We should be looking for like for 6, in order for 6 of the up to 10 possible numbers to meet our criteria. There we go. It's 0, 1, or 2 if we're looking for an 8 prime value family. If we're looking for 7, it would be 0, 1, 3. If we're looking for 8, which is the actual stated problem, it's 0, 1, 2. So 10 minus this target. For 6, for a limit of 100. 7 for limit of 100,000. 8 for limit of, we don't actually know yet, but guessing 1 million. Not something we have to worry about right this second, obviously. So we're gonna say smallest prime is equal to 0. And then we're going to say family is equal to this. Actually, we'll just say family equal to that. And then we'll sort it. Okay, Well, that's fine. We just haven't written out our if block yet. Maybe I do want to have a smallest prime here. Okay, so find if I has... Ooh. So this step we're actually going to skip for the first one. Because obviously we're not looking for 2 plus of the digit. And what we can say here is if this way, if star string I ri dot sort actually I'm gonna make string I be a thing. And then I'm going to say for digit in string I, and then let's see, do we have a replace digit with 0 and then family dot append okay, so does this change string? Return a copy. Okay, that's ideal. And then for D in range 10, we're basically going to replace the digit with D, which in some cases will probably okay, and then we do this part right up in here. And we actually want this to be an integer, so is prime num false. If is prime num, then if not found smallest, smallest prime equals num, found smallest equals true, and num primes plus equal 1. And then we're going to say if num primes is equal to the target break. Now that will only break us out of this for loop. So let's go ahead and move this up 1 and have this same break here. Probably not the best way of doing this part, but I know that it works. So let's go ahead and run, see if we have any problems. Okay. I am confused. So it's saying that replacement argument 2 must be a string, not an int. Oh. That's fair. Okay. So. That does not quite work. Let's go ahead and see how it works for 100,000. As that is actually more important for our use case. Okay. Let's see, start equals 0 if length string I actually, let's do this a different way. Oopsies. Let's see. I'm gonna go ahead and do an if new less than I. Let's try that and see if we can get the correct answer. No, that isn't right. That isn't right at all, is it? This needs to be there also. Okay, so that got us to the correct answer, at least for the 7 primes version. Because... yeah. Okay, so basically what we did is made it so that when we get to, like, 13, we don't then start counting 3, because it's a fewer digit number. Effectively removing... let's just replace the first digit. Okay, so... let's go ahead and up this... like, maybe we don't need this step. Maybe this step is entirely unnecessary since it worked for, like, 56003. Let's go ahead and make this 1 million and get a target of 8. Let's see how long it takes and what we get. Okay, so it took a second. Honestly, closer to half a second. And we got these numbers. So the ones being replaced with 2s. 3s, 4s, 5, 6, 7, 8, 9. So let's see if this is our correct answer. Alright. So that is the correct answer, and obviously this whole step, completely unnecessary. And since it did solve in under a second, obviously well under our limit. I'm just going to remove this formatting because we don't actually need it. Do all possible replacements and check how many are prime. Okay, so we actually did follow the notes here, but I noticed this pattern and I was like, oh, maybe I should do this, care about this pattern, but it didn't actually end up mattering. Instead, we just find the other numbers in the family, count how many are primes, and break if match target. And then this just keeps us from continuing to try again. Okay. So, yeah. All we did is we said, okay, for if this number is prime for I from 0 up to the limit, if the number is prime, make a string version for every digit in the string version, digit being a string now. Look at 0 to 10, or 0 through 9, I should say. Replace occurrences of the digit in string 1, string I, with that digit, and then if the new number is greater than or equal to I, we append it to the family. If it isn't, we don't, to prevent cases with a leading 0. I suppose I could also... Well, casting it to int will remove the leading 0. But another way to do this would be to just say if new starts with 0 or does not start with 0, and then cast it to an int down here. But this seems to work very, very efficiently, so it's fine. I think this also prevents us from, like, too much rechecking of the same number, but I could be wrong. So yeah, and then we just go through and we count how many primes are there. We take note of the smallest prime, which honestly we shouldn't have to do. This whole part we should be able to just remove. Smallest prime, let's go away. And actually, let's just delete this whole part, because the first one is always going to be the smallest. Same correct answer. Okay. I'm gonna call that there for today. We did a little bit of refactoring, realized we didn't need all of the logic we had planned to write. And yeah, that's it. I'll catch you in the next one.